Hello. So let's start the explanation of the previous video that how to find the bridges of the remaining part. So we have seen that these are the three cases that we are going to have. First case, either while traversing any node, either that child is its parent or its child is already visited, means that is a package. Then we are going to do this step. Or either it is not visited, then we will call a DFS to that node, and after calling the DFS we will be doing these things. We will be checking if that edge that we have called is a bridge or not. For that, this is the condition for checking the bridge condition. I am writing it here, bridge checking condition. This is bridge checking condition. This is the updating the load time of node if it is package, updating load time if it is package, if it is package, and this is the thing that we updating the node if it is forward edge, updating while tracking back, updating node if it is forward edge while tracking back. While tracking back means when the function call is over, then we are doing this thing. So let's come to the example. These are the three things that we are doing, and when the DFS call is needed, we are doing three things. We visit that node, we are updating the end time and the load time of that node to the equal to timer, and we are incrementing the timer. Okay, so this is the graph that we have. This is the end time vector, this is the load time vector, this is the stack, this is visited vector, and this is the timer variable. So let's suppose we have called DFS1 from the main function, and we have two arguments that we have to pass. The first one, see, there are two arguments. The first one is the node itself, and the second one is its parent. Okay, so from the main function, suppose we have called the DFS1 minus 1, means 1 has no any parent. This is the root, so we have initialized the parent of 1 with minus 1. Now after that, what will it do? We will visit that node first. So DFS of visited of 1 will be changed from 0 to 1. Visited array will be initialized with 0 all. Whenever we will visit, we will put value 1 there. We will put the timer of in time and load time equal to the timer, and we will increment the timer to 1. After that, we are going to traverse the edges connected to 1. So we suppose we traverse this edge, we come here, because since it is not visited, then it will come in this condition, second case here. So second case here, I am writing it, second case, no need to write, just stand. By second case, this will come in the second case condition that it is not visited. Since it is not visited, then it will call a third case, sorry, it will come in the third case. Since it is not visited, it will call a DFS of child and the parent of that. So DFS of 2, 1 and its parent is 1. So when the dfs of 2 comma 1 is called, then it will first visit that node. After that, it will in time of that node, in time of 2 is equal to timer is equal to load time of that node, and we increment the timer by 1. Now check the adjacency list of 2. Suppose it comes check and goes to 1. Since it is the parent of 1 is the parent of 2, so it will continue and it will do nothing. After that, it will come traverse the second edge, that is this one. Since it is not visited, so it comes in the third case condition, that it is not visited. Then it will again call the dfs from that condition, that dfs of 3 comma 2. Then it will visit that node. In time and load time will be of 3 will be equal to the timer. We will increment the timer by 1. Now it will check the adjacency list of 3, and in the adjacency list of 3, 2 is there, but since 2 is its parent, so it will do nothing. It will continue. It will come to 4. It is not visited, so this is the third case, that it is not visited. If it is not visited, then what we were doing, we were just calling a dfs function, and after the completion of dfs, we will be using applying the further steps. So dfs of 4 and its parent is 3. Now it will come to 4. Then it will first visit that node. In time and load time will be equal to the timer, and the timer will be increased by 1. Now it will start traversing the adjacency list of 4. It will come to 3, but since 3 is its parent, so it is going to do nothing. Now this is the interesting part. Now after that, it will traverse 2, but since 2 is already visited, means this is what? This is back edge. So if this is a back edge, means this is the second condition. This condition, else if condition, is there. If it is already visited of 2 was already 1. See here, visited of 2 was already 1, visited vector, means this is the back edge. So if this was the back edge, then what we were doing, we were just updating the load time of that node. The load time of that node, how we are incrementing the minimum of the load time of that node, and the in time of the already visited node. So the in time of the 2 is 1. See here, in time of 2 is 1, and the load time of node 4 is 3, so minimum is 1. So it will be updated to 1. Okay, now see why we are updating this load time. If this edge, if this back edge was not there, then the load time of 4 would have 3, which means that we would have equal to the in time of node. But since there is a back edge, means this is connected to the ancestor. We are checking it for a bridge. If it is connected to the ancestor, then something representation should be there that this is connected to the ancestor, and this cannot be the bridge. So we are updating the load time to the in time of that node, so that we will be able to check that it is not the bridge. There is another path from which this node is connected, and even if you break this node, it is going to do it, nothing will happen to him, nothing will happen to 4. So there is another path from which it is connected. For that purpose, we are updating the load time, and while returning also we will update the load time of each node. As there is another path, if there is another path is exist for 3 also, the see this path is exist from 3 to 4 and then 4 to 2, this path is existing. So even if you break this edge, it is going to happen nothing for this graph. This will not act as a bridge, this edge will not act as a bridge. So we will be updating the load time of each node every time we trace back. So the load time of this is updated here. Now since the adjacency list of 4 is completed, so it will come back to 3. This call is over, it will come back to 3. Now what the things that we have to do after it was called from the main function, dfs 4,3 was called from the main function from here. See, this was called from here. Now it will check for this node. If it is while traversing back, it will check back for this node. If that was not the bridge, so for checking the condition, this was the condition for checking it if it's a bridge. If load time of x, what was x? X was here 3. X was here 3, and so the load time of 4, load time of x, see the condition here. The condition is that the load time of x is greater than in time of node, then that is a bridge. So is that the case here? The load time of 4 is 3 and the in time of 3 is 2. So it load time of is not greater, load time of 4 is not greater than 3, hence this is not going to be the bridge. We have checked this. After that we will update the load time of this node also, because if this node is connected to the ancestor, then indirectly this node is also connected to the ancestor, which indirectly its parent. So we will update the load time of this node to the minimum of the load time of this node and the load time of this x. So this is the statement here, load time of node is minimum of load time of node and load time of x. So we have updated its load time. So let's update the load time. What it will be? It is going to be the 4, it is going to be the 1. How? Minimum of load time of 4 and load time of 3 is 1, so it is load time of 3 will be 1. After that dfs 3.2 is remaining. The steps after calling the dfs 3.2, all the edges connected to node 3 has been already traversed. So after dfs 3.2, what we will do, we will check if this edge is not a bridge. So we will check the same condition here. We will check the load time of the 3 is greater than the load time of 3 is whether it is greater than or less than the in time. So check the load time of 3 is 1 and in time of 2 is also 1. Since it is not greater, so it is also not going to be the bridge. After that we will do, we will update the load time of this node using the minimum of load time of 2 and the load time of 3, which is 1, so it is 1. This work is over. It will come to dfs 2.1. All the nodes connected to this has been traversed. 24 is also traversed. 23 is also traversed. 21 is also traversed. So after that, what we had to do? We had to check if the this is a bridge or not. So load time of 2 is 1 and the in time of 1 is 0. Means load time of 2 is greater than in time of 1. Means what? This is a bridge. How we are saying that this is a bridge? Because it is not load time of 2 is greater than the in time. Means this node, this second node is not connected to anywhere in the ancestor. If the load time of this node is smaller than this time in time of this node, then it signifies that this second node is connected somewhere to its ancestor, but since it is not connected to its ancestor, means this is a bridge. So from 1 to 2, this is a bridge. This is how we can identify the bridges is there in a graph or node. This is the method using the load time and the end time. And you have to just remember two things. Just remember or just understand it well. Two things. The condition for the bridge checking condition, updating the load time if it is a package, and updating that node load time also since it is indirectly connected to the ancestor. So this is how we we check whether there is a bridges inside that or not, and we can do many things with that concept. So hope you have understood.